Hello students and welcome back for our third and final lecture on radical reactions. So in this last lecture, we're going to talk about polymerization reactions, which are very important for industrial production of lots of important products, such as all plastics and also PVC, piping, for example, for the water in your house and the drains and much more. We're also going to talk about applications of radical reactions to synthesis. So, um, free radical reactions are used to create polymers. Polymers are those molecules that have many repeating units joined together. So you may have heard of a type of plastic called polyethylene. Um, Ethylene, or as we call it, ethine, is C2H4, right? And so we would call it ethine by the systematic name, but it's very commonly called ethylene, C2H4. And basically, what we can do is have a situation where the double bond, just very simply, goes away if you have a neighboring molecule here. Neighboring ethylene molecule. Essentially, what goes on is this bond goes away, and then you end up with a bond to the neighboring carbon, and then this goes away, and you're going to get one going on and on and on and on. And so notice what that means is you have two carbons with a single bond and then two hydrogens on each one, and that repeats and repeats and repeats. And the way that's shown as a shorthand is that we have the two carbons, each with two hydrogens. We put a bracket around them with lines saying this is going to keep going on and on and on many times. And we often put an N here, which says this goes on N number of times, or if you just leave N, it means many. And this is what's referred to as a polymer. It has many of these C2H4 repeating units over and over again in a long chain. So how does it happen? Well, first of all, like all of our radical reactions, we need some type of radical initiator with a weak bond that we can break with heat or light. A peroxide, which we abbreviate as ROR a lot of times, just focusing on the oxygen-oxygen bond here. That breaks in a homolytic bond cleavage, and we get two of these radicals, these oxide radicals. Then we have some product, or some reactant rather, that has a carbon-carbon double bond, and so this radical does an addition, and so one electron from the pi bond and one electron from the radical here form a bond to this carbon, and then one of those electrons is left behind, form this carbon radical here. And then this can occur again and again and again. So we have this alkoxy radical here. This goes and does an addition on a neighboring pi bond here. And so we get, again, the one pi electron and one radical electron produce a bond, and then we have one electron left. And we have a radical, and this continues to go on and on, lengthening the chain until it's maybe, thousands and thousands, maybe hundreds of thousands of carbon atoms long. Finally, at the end, we'll get coupling. So the coupling, there's a couple of types of coupling that can occur. We can have a coupling between the alkoxy radical and the alkyl radical here, and that will produce a product with the ether on the end here. Or we can get a coupling between the two alkyl radicals here. So when this happens, it doesn't always happen in just one straight chain. What often occurs is that there's branches in the chain. So you can have, in the middle of this reaction, you can have one of the radicals that's been produced perform a hydrogen abstraction, producing a radical in the middle of the chain. And then when that goes and does an addition, so here the next step here is an addition. So this is a hydrogen abstraction. We're removing a hydrogen. And then we have the radical left over here. And then now this radical can react with the abundant, alkenes that are the main reactants in this reaction and do an addition. And then we have a branch here, and that branch can lengthen as well. So that branching can be controlled by the reaction conditions. If you're keeping a lot of these radicals around, you begin the production of a radical that can produce a branch. And then adding more reactants, those will be extended. So if the reaction conditions are maintained such that we get highly branched polyethylene here like this, that gives you your more flexible plastic bottles. Uh, and so that's like the in your water bottle. That's the main part here. So if you're looking at your water bottle, here's your water bottle. It's kind of like, it's whatever. It's got like little ridges usually, so you can squeeze it. And then you have on top of it, you have a cap. Uh, so the cap is very hard, and if you smash the bottle with a hammer, it's just going to deform, right? And so this this part, the highly branched ones like these are going to be this part of the plastic bottle, and then the straight chain ones are going to be the cap part right here. And the reason why it's brittle is because when you have the branched ones, all these hydrocarbon chains kind of wrap around each other like spaghetti. And so you end up with this kind of mesh, like think of a mesh of string or something, like a ball of string. It's kind of squishy and soft. Whereas when you have these straight chain ones that are mostly straight chain, they're just on top of each other and they have some attraction, but if you can easily break that by smashing it. Um, Now, polyethylene is not the only polymer. It's the most common. If you see, I think I have the. If you look on your plastic bottle, there will be a code. If it says number 1 in it, it's polyethylene. And these go 1 through 9. There's various different polymers that can be recycled. But if you see the 1 in your recycling symbol, that's a polyethylene. There's also polypropylene. So the difference here is the monomer, the reactant molecule, instead of being just ethene, whoops, there is a there we go. There is a another carbon attached here. And so when we have the repeating unit, this is going to make the one with a carbon with 2 hydrogens attached right here. And then this carbon will have a hydrogen and a methyl group attached. And this will go on and on. This is used for like carpet fibers, sometimes in various appliances. So this is kind of like a more kind of solid. If you have it really thin, it gives you that solid structural material for the carpet. It's kind of tough. If you have it on a appliance, it's usually not in small fibers. It's a thick piece, and it gives it that kind of plastic texture you're used to. There's also polystyrene. So styrene has a reactant molecule that has a phenyl or a benzene group. Remember, the phenyl means the benzene group. So we're benzene ring. So we're talking about like this. So when we say pH, we say this pH, abbreviated. And so this has this benzene rings hanging off, and you can see that has an impact on the composition of the polymer. This is used for styrofoam, and so that has kind of softer type of easier, more malleable properties here. That's also because it's puffed up with air, but it's polystyrene, like your packing materials and your soft styrofoam cups and stuff. Vinyl chloride, extremely important monomer uh, for for polymerization. The polymer polyvinyl chloride, or PVC, it's used for the drain pipes for almost all of our homes now. Also, for many of us now, the new houses, even their pressurized water lines that are coming in are a type of PVC, in which the reaction conditions have been controlled to make it very tough. Uh, and this is produced again from having the chlorine attached to the carbon-carbon double bond here. So one carbon in the monomer has 2 hydrogens attached. The other carbon has a chlorine and a hydrogen. And this, of course, gets involved in a chain that goes on and on and on, like all polymers. Finally, we can use tetrafluoroethene to produce Teflon. So this is a polymer composed of that. Again, each carbon has 2 fluorine atoms attached here in this polymer, and the chain goes on and on and on here. This is the non-stick coating Teflon that's so famous and used for almost everyone's frying pans for eggs and stuff. So that's one of the most important industrial applications, the formation of polymers. That is a radical process. Also, a radical process, like I mentioned on the first slide in these lectures, is hydrocarbon refining. So oftentimes when we get hydrocarbons, they're not all the size of hydrocarbon molecule that we prefer. We use a lot of hydrocarbon molecules that are in the 8 to 12 carbon range. They're used for gasoline and liquid fuels. The other ones are less used, but they're still significant. So the smaller ones are still significant. They're used. Methane is used for heating our house and operating. It's what we call gas, our gas line, our heater, our stove, all of that. The larger hydrocarbons don't have as many uses. They are used for petroleum jelly, but we use a lot more gasoline, oven, stove, methane, gas than we do these larger hydrocarbons. So when this raw crude oil comes out, what we want to do is take those larger hydrocarbons and turn them into smaller ones. And that process is called cracking to produce smaller alkanes and alkenes. And the way that it works is we heat these up until a hydrogen pops off or something breaks, and then this produces a radical, and that radical can be involved in a reaction in which we form a double bond from the radical and one electron in a neighboring bond, and then we have the cleavage of the bond to produce a smaller radical here. And we have this propene here, which is very useful as a gaseous fuel. We can burn this. Hydrocracking can also be done. So we do this in the presence of hydrogen. This will produce for us unsaturated hydrocarbons, which is usually what we're looking for in terms of fuels, like 1, 2, 3, 4, 5, 6. We want something like this, or maybe a little bit longer to be our gasoline. This is propane. We can use it in our barbecues and stuff. Some people operate their whole house off of propane. Another process here is called reforming, which is also a radical process. This takes this will produce branch chain hydrocarbons for us. This is octane 1, 2, 3, 4, 5, 6, 7, 8. This is octane, and octane has an octane rating of 0. Actually, you might have seen this as a pump. Straight chain linear octane is an octane rating of 0. So this is not good for gas. 0 octane is what we call this, meaning it's straight chain octane. What we'd rather do instead is have more branches. So if you use the same process and you get a hydrocarbon, a radical branch in the middle, you can have coupling reactions that produce branch hydrocarbons. And so this would be much higher octane. So this would be great for fuel. This is a kind of octane that's branched that would be good for gasoline. This one would produce engine knock. It would not be as good for gasoline. So reforming is important as well. Finally, let's talk about synthesis. So the most important reaction for this in terms of synthesis is to take a hydrocarbon, which hydrocarbons are generally unreactive, right? These are the only reactions we've seen in the entire class that involve just a plain old hydrocarbon with nothing else. Hydrocarbons are spectacularly unreactive, which in some ways is good when it comes to plastic, for example. Our polymers, which are all, polyethylene, all carbon hydrogen bonds, spectacularly stable. That's great. Or we can stick something in a plastic bottle and we don't have to worry about it undergoing reactions. It's just going to stay in that plastic bottle. Will be fine for the most part, unless it dissolves the plastic or something. But chemical reactions are not likely to occur. The downside of that is plastic, for example, sticks around forever. It never reacts, right? And so if we want to do synthesis, an alkane is not very useful for us for synthesis because it's hard to make it react and produce something else. And the reason is because reactions are generally initiated by some nucleophilic attack or something like that, right? Or at least that's a part of them. And that needs a polar bond to occur. All the reactions we've been doing, they occur because there's a positive and a negative part, and the negative part goes for the positive part. In a hydrocarbon, there is no negative or positive part. It's all nonpolar. So if we want to use this to make for chemical synthesis, we need to introduce a polar bond. And that's what halogenation is for us. So that's going to be the key reason that we have halogenation in our synthesis steps. Is if you're starting with a hydrocarbon, you should think, okay, my first step is probably going to be to create an alkyl halide so I can do a substitution or an elimination. Okay, and so we would do Cl2 or Br2 with light, and that will produce the halogenated product. Remember that bromination is much more regioselective. It's going to go on the tertiary carbon if there is one. If not, it'll go in the secondary carbon or the allyl or the benzyl carbon. Um, and so the chlorination here, this can happen anywhere. The bromination is going to occur primarily on the most substituted carbon, almost 100%, very, very strongly. So that's something to keep in mind. You can direct in general, what that means is the bromination. This is going to be your preferred method over this, because you can tell where the bromine is going to go. And so this is going to be the one that you're going to use. It is slower, but it's more selective, which is often nice. Now, practically speaking, remember we talked about bromine and how we do have to worry about if there's a double bond, the bromine can do an addition reaction on the double bond. So practically speaking, what we're usually going to do is instead of Br2, we're going to be using NBS and light. So this is going to be the reagent that you're going to want to have. You do have it in your notes. This is the one you're going to be using very, very often. And so, as it says, this functionalizes an unreactive alkane. That's the fancy way of saying it. It takes something that's not reactive and it makes it into something that we can use. And so, if we use NBS, N-bromosuccinimide, and light, we can put the bromine in the most substituted carbon. And then we can perform a substitution with some other nucleophile. Or we can do an elimination if we have a base. And then we can go on and do our synthesis. So this is when you see a hydrocarbon, you should be thinking NBS, HNU. That should be your reagent. And then you'll go from there with substitution eliminations. So a summary, these are the new reactions in this chapter. Now, they're not all new. We've seen this reaction before, right? The difference is now we can reproduce the mechanism that shows why the bromine attaches to the less substituted carbon. You do need to know the mechanism. Know the mechanism. It's the most important mechanism in the chapter. Okay. Allylic bromination. If you have a double bond and you want to halogenate, you must use NBS. Otherwise, you will end up with an addition, right? If I were to go Br2 here, then what am I going to get instead? I'm going to get, right? So we don't want to use Br2. We want to use NBS with H. And that will put the bromine at the allyl position, one carbon away from the double bond. And then finally, we can also brominate with Br2. But you don't want to use that if there's a double bond, okay? But you can always use it if there's not. And that is it for the radical chapter. And so now, again, we have explained this reaction. You do need to know the mechanism, the full explanation for it. But these are our three main reactions. What's most important in this are these big ideas about stable radicals, why they're stable and so forth, and the way that these reactions occur in their three radical reaction steps: initiation, propagation, termination. Okay, and that's it for this week's lectures, and good luck on the homework. Let me know if you have questions. I want to help you. All right, have a good one. Bye-bye.